teacher. Welcome to my video. Today I'm going to dive deep into homework 4, analyze the given codes one by one, and understand their time complexities. When writing code, it's not just about making it work. The real question is how fast does it work? Because a poorly optimized algorithm might seem fine for small inputs but can turn into a complete disaster with large datasets. That's why we use big O notation to analyze the efficiency of our algorithms. Now let's examine each code snippet step by step and break down their time complexities. And first of all, I will start with what is the time complexities of the following function. And let's take a look at the given function on the screen. We can see that it contains a loop structure that runs for a certain n times. First of all, you're writing a result integer equals to 0, and then here writing a for loops, and if I equals to 0 and I smaller than n, and I plus I equals to new I, and if I smaller than 0, result plus equals to ri times ri, and then it's continue to I equals to n, and then returning result. Since a constant number of operations are performed in each iteration, the total time complexity of this code and on. But what if we add another nested for loop inside this one? In that case, each loop runs n times, leading to a total of n times n equals to n square operation. That would make our complexity O n square. The key takeaway here is that analyzing loop behavior is crucial for understanding algorithm efficiency. And then that's okay. Let's continue with another question with what are the time complexity of the following code fragments. Now we have different code snippets, and our goal is to analyze their executing times. Let's go through them one by one. First code snippet is here, and then here writing for loops in I equals to 0 and I smaller than n square n times n, and I plus I equals to new I, and then return key plus plus. This snippet contains a single for loop that runs n times. Therefore, the total number of operation is n, and the time complexity as is on. And then I will explain this part. This part is writing. This part is like here first code. These codes are similar, and then second code snippet. This code has two nested for loops. The outer loops runs n times and the inner loop also runs n times. Since the inner loop executes fully during each iteration of the outer loop, the total number of operation is n times n equals to n square. Thus the time complexity of this code is O n square. And then here has for loop and here has for loop, but they are similar to this code. Here has only two for loop. As we can see, the way we write our loop significantly affects the speed of our code. That's why we should always aim for efficient implementations. And let's continue with what is the time complexity of the following power function. Let's analyze the executing time, and we're writing a long method, long recursive power, long x and long n, and here writing if method. If n equals 0, return 1, and if n equals 1, return x, and if you're writing returning recursive power x times x and n division 2, and then this code will finish and returning recursive power this one. If this function multiplies x by itself n times, each iteration performs one multiplication, meaning the total number of operation is on. On is this one. I will show that. On is this one, right? Let's continue. However, if we use a more optimized approach that divides n by 2 in each steps, like in power x and division 0, then the number of operation is greatly reduced. In this case, we get a time complexity of logarithm n, which is significantly better. This shows us that choosing the right algorithm can make our code much faster. And then let's continue with what is the time complexity of the following Fibonacci function. Fibonacci function is writing in here, integer recursive Fibonacci integer add. If n smaller n equals to 0, return 1, and returning recursive Fibonacci n minus 1 plus recursive Fibonacci n minus 2, and each call to Fibonacci n makes two additional calls, Fibonacci n minus 1 plus Fibonacci n minus 2. So the number of function calls doubles at each step. This results in a time complexity o 2 square n, which grows exponentiation and becomes extremely slow for large values o n factorial n, sorry, not factorial. However, if we use dynamic programming, we store the values we have already calculated, preventing redundant calculations. This improves the complexity to O n. I think that's okay. And then let's continue with faster computer or algorithm. And then this one is, yes, last exercise. Now we have continue this part. We have two algorithm. One runs in ON while the other runs in ON square. But the ON square algorithm runs on a faster computer. Which one will perform better, you think? For example, if n equals to 1000, an ON square algorithm will perform 1 million operations, while an ON algorithm will perform only 1000 operations. The key takeaway here is that a bad algorithm remains bad even on a fast computer. That's why choosing the right algorithm is far more important than simplify having powerful hardware. And then I think this part is okay. Okay. Today we took a deep dive into time complexity and explored why algorithm efficiency is crucial. We saw that writing efficient code is just as important as writing correct code. And then thanks for watching my video. Have a good day. Bye bye.